All right, the last application of three dimensions that we will cover in this course is going to be a concept called total differentials. And just like all the other applications in three dimensions that we have talked about, this is really just an extension of something we already did in two dimensions. Okay? We did differentials in two dimensions. Okay? And let me just remind you of a situation. Just to pick a really easy example, if we had the equation y equals x squared, and we wanted to see what would happen at the ordered pair 2, 4 if we let x change by a half a unit, for example. Okay, so 2, 4 is definitely an ordered pair on this graph. And if I let x change by a half a unit, so in other words, if I let x go up to 2.5, we can use derivatives or differentials to approximate what that question mark should be, what that y value should be. Okay, here was our process. Okay, when we took the derivative of the left side was just dy dx, and the derivative of the right side was 2x. Okay? But what we said is we can take this rate of change, and at least mathematically, we can move that dx or multiply that dx across. So that if I want to approximate how much the y value has changed by, all I need to do is take 2 times my x coordinate times my dx value. Okay? And so from up here, I would take 2, the x coordinate that I started at was 2, and my dx was a half a unit. I went from 2 to 2.5. And if I multiply all this together, 2 times 2 times a half, well, that's just 2. And so I could guess that if I plugged in 2.5, where would this value be? Okay. Well, it was at 4, and we let it change by 2 units, so where is it at now? 6. Sure, 4 plus 2 is 6. So we guess that if we were to take 2.5 and square that number, that answer is going to be really close to 6. And notice we didn't have to do anything on the calculator. Okay, we're just making an approximation that it's really close to 6. Okay? All right, so that's what we mean by differentials in two dimensions. Now, all we're going to do today is we're going to extend this idea so that we can look at what if we want the x value to change by something, and what if we want the y value to change by something, and we want them to change at the same time. Okay? How's that going to affect the z coordinate if we let more than one thing change at once? Okay? All right. So my first example that we will work is this one right here. Okay, what if we want to approximate this value? 2.1 squared raised to the 1/3 power. Now again, now that we have calculators, we would sub this into our calculator and we'd come up with the result and we're finished. I mean, there's no need to do differentials on a problem like this, but it's a good example, a very simple example of how we can use differentials so that when we get to the more complicated problems, we see how the process works. Okay? What we're going to do is we're going to first of all try to pick out some really nice numbers that these are close to being. Okay? So for example, I'm going to pick out some nice numbers. Well, this is really close to what nice number? Close to 2. This is really close to what? 2. So I'm going to let my x value be 2, and I'm going to let my y value be 2. I'm going to pick some nice numbers here so that when I rewrite this equation as x squared plus y squared to the 1/3, I'm looking to be really close to 2 and 2 for x and y. Now, let's go ahead and find the z coordinate right away as well. Okay? If I plug in the nice numbers, if I plug in 2 here and 2 here, okay, what's the value of z? Okay, it is 2, right? Because 2 squared is 4, another 4 is 8. The cube root of 8 is 2. Okay? So I'm starting at the order triple 2, 2, and 2. Now, what I want to do is I want to see how can I use derivatives to approximate this z coordinate over here. Okay? All right, well, we use derivatives to follow this process. Now, the only thing is, since we have more than one variable, we won't just use a full derivative, we're just using a partial derivative. Okay? Just like we've been doing this whole chapter. All right, so the process will look like this, or the formula will look like this. If I want to approximate how much z has changed by, I'm going to take the partial derivative with respect to x, and multiply that by dx. You know, kind of like we did over here. We take the derivative multiplied by the variable we took the derivative of. Okay? And then plus the partial derivative with respect to y times dy. This is our formula that we'll use throughout the day today. All right, so my first question, what's the derivative of this function with respect to x? I've got something to the 1/3. So what's the derivative of something to the 1/3? Okay, 1/3 times all this to the what? Negative 2/3. I just take away a full unit. Okay, I've got a chain rule in here. So I take the outer derivative, 1/3 times all this to the negative 2/3. And then what's the derivative inside if I'm looking with x as the variable? 2x. Sure. And then when I'm finished, all I do once I have the derivative is I multiply that by my change in x, dx. Okay, so dx. Okay. Plus, now I need to do the same thing with respect to y. The derivative is going to look almost exactly the same, except the chain rule will be a what this time? It'll be a 2y instead of a 2x. Sure. Okay, so I'll just rewrite this. 1/3 x squared plus y squared to the negative 2/3 times dy. Whoops, 2x. 2y dy. There we go. Okay, and now it's just a matter of us subbing in the appropriate values into this equation to come up with what the value in z should be. You know, how much is it changing by? Okay. All right, so this is just a 1/3. Okay, now these x's and y's, these are the nice x's and y's. This is the point that I'm starting off of, is 2, 2. Okay? So if I sub in 2 in both of these locations, this is an 8. 8 to the negative 2/3. Okay, well, let's do it this way. What's 8 to the, if I take the cube root? That was 2. If I take 2 and square it, that's 4. And if I have a negative power, that just moves it to the denominator. So this turns into a 1/4. Okay? If you need to, you punch it in your calculator. Okay? 2 times x is just 4 because x is 2, so 2 times 2. And then what's my dx in this problem? I haven't defined it yet, okay? But what is happening to the value of x as I try to get down to this location here? It decreased by how much? 0.08. So my dx in this problem is negative 0.08. Okay. All right, and then I keep subbing in on the second part. 1/3. This is still a 1/4 right here. 2 times y is still 4. And what is dy in this problem? .1. Good, because I'm going from 2 up to 2.1, so I have changed in the positive direction by a 1/10 of a unit. Correct. Okay? And now I'm going to calculate all of this. Okay? First of all, I see the 4 and the 1/4 multiplied to just be 1, so I don't have to really type those in. Okay? This is 1/3 times negative 0.08, and this is 1/3 times 0.1. Okay? Definitely I can factor out the 1/3. I'm trying to do this without the calculator. Okay? 0.1 minus 0.08. 0.10 minus 0.08 is what? Oh, 2. Sure. 10 minus 8 would be 2, so 0.02. And if I was to divide this by 3, well, that's a little bit harder to do because dividing by 3 is not the nicest thing. Okay, but 0.02 divided by 3. Okay, 2/3 is just 0.6666 forever. Okay, so this answer would be 0.006666, going on forever. Okay. All right, now, this has told me how much the z value needs to change by. So what is my final z coordinate up here? What's the final answer to the problem then? 2.006666 going on forever, right? Because I was at 2, and I've now needed to change by this much. So my final location is 2.006 repeating. Okay, so really close to 2.01. Now, If you want to test this out on your calculator, go ahead. Just punch this into your calculator as it is, okay, and see what answer you come up with. And my guess is that the answer will be very close to 2.01. Okay? All right, so that's one way that we can use differentials. And again, the big advantage of differentials is that notice we could let more than one variable change at the same time. Okay, we let the x change, we let the y change, and we can look at that total change, which is the reason they call it a total differential. Okay? A lot of things in the real world, we can't just isolate and let one thing change. There's going to be more than one thing changing at the same time, so we have to be able to look at the total change or the total differential in the situation. Okay. Next example here. This one will actually be a little bit easier than the one we just did. What if we look at estimating the value of 1.02 e to the minus 0.03? Okay, maybe I should have started with this one first, but this will be all right. Okay, to begin with, what's the equation that I want to use? Here I decided that, well, this wasn't a very nice number, so I put in a variable. This wasn't a very nice number, so I put in a variable. This was a fairly nice number, so I just left it. Okay, so what about over here? Okay, pretty nice number? Not really, so what I do, I go ahead and sub in a variable for it. Let's let that be x. Okay, e is a pretty nice mathematical number, so we leave it, and is negative 0.03 very easy to calculate in our head? No. So we go ahead and we change it to another variable, y. Okay. All right, so this is our basic function. Now, what's the ordered pair that I want to start at, or the ordered triple, I guess? Okay. X is really close to what? Really close to 1, so I let x be 1. Y is really close to what? 0, so I let the y-coordinate be 0. And if I let x be 1 and y be 0, what's the value of z? It should be 1, because anything to the 0 power is 1. 1 times 1 is 1. Okay? So I'm going to be really close to a z value of 1. If I plug this in my calculator, I'm going to get an answer really close to 1. But it's not going to be exactly 1, so we want to find out how much it's off. What's the change? Okay? So we'll go ahead and use our dz formula from the previous example. Okay? What's the partial derivative with respect to x? If x is the variable here, what's the derivative? E to the y. Good. Okay? E to the y is constant, and x is it's kind of like a linear term almost. Something times x, the derivative is just the something. Okay, so e to the y times dx. Because I took the derivative with respect to x, I multiply by the change in x. Okay, plus the derivative with respect to y is what? Well, first of all, x is a constant, right? So x stays there. And then what's the derivative of e to the y? E to the y. Sure. Okay. And then I multiply by dy. Okay. All right, now let's go ahead and approximate this value of dz. All right, e to the y, so that's e to the 0. Okay, what's dx in this problem? How has x changed if I start at the nice point and I go to the one that's not so nice? 0.02. It's gone up by 0.02. Sure. Okay. Plus x is 1, e to the 0, and then what's dy? If I start at the nice point and I go to the one that's not so nice. Negative 0.03. I started at 0 and I went down to this, so I'm down at negative 0.03. Sure. Okay, and now I make this calculation in my head. Okay, e to the 0 is just 1. This is just a 1. So basically I'm doing 0.02 minus 0.03. So it looks like negative 0.01. Okay, so if I was at 1 and my change is this, What do I approximate this answer to be here? If I was at 1 and my dz is this, where am I at? Yeah, 0.99, right. Okay? If I'm at 1 and I change by this much, I lose 1/100th, I'm now at 0.99. And again, you want to double check this, go ahead and punch this in your calculator, and the answer should be very close to 0.99. Again, the advantage is that we really didn't have to use the technology to do this. Okay? All right. Now, some other types of examples that I want to go through here. Let's look at this question right here. All right, this is a word problem question. I'll go ahead and kind of read it through here. Okay. It says that this function finds the number of liters of blood pumped through the lungs in 1 minute. Okay? So C is liters of blood per minute, basically. And then there are some other variables, and this question doesn't say what A, B, and V are, but those are variables dealing with the, how much blood can be pumped through the lungs in a minute. Okay? It says, suppose A is 160. Let me just do it this way. Okay, A is 160, B is 200, and V is 125. Okay, and then this will be a C value out here at the end. Okay, and they say estimate the change in C if A becomes 145, B is 190, and C and V changes to 130. So what if we let all of these changes take place? Okay? How does that affect the value of C down here? Okay? All right. And like I said, we can use differentials to make this approximation because it's a lot faster on computer systems to calculate differentials or do derivatives than it is actually to plug values into functions. Now this one I could be wrong on that because there's no squareds or higher powers on this. So a computer could run this one through pretty quickly. Okay? But for more complicated equations, it is faster to use differentials. Okay? All right, so let's work through this here. Now, our formula this time will look like this. We just have extra variables this time. Okay? dC will be the partial derivative. Let's do it this way. The partial derivative with respect to A times dA plus the partial with respect to B times dB and the partial with respect to V times dV. So we just have an extra variable in this function, but it's the same process that we just did on the previous two examples. All right. The hard part is going to be doing all these partial derivatives. Now, my recommendation would be this, is if we're going to take the derivative of this function, usually let's just move this up into the numerator. It's easier to work with this. Instead of doing quotient rules, let's just rewrite this as b minus v to the negative 1. Okay, I think that'll be easier to take the derivative of. All right, I want the derivative of that function with respect to a. All right, so a is my variable. Okay, what's the derivative with respect to a? Oh, you know what? Just a second. Let me back up here. I copied this problem down wrong. Okay, the a and the b are switched here. Okay. We'll still do the same process on our derivative here. And it may actually not even change the answer, but I'll go ahead and do it right here. Okay, it's really b over a minus v. Okay, I want to know the derivative with respect to a. Okay, so what happens to the b? It's just multiplied so it stays there, right? Okay, so the b just stays there. And what's the derivative if a is the variable here? Well, the negative 1 comes out front. So negative 1 times a minus v to which power? Negative 2. And then what's the chain rule inside here? What's the derivative of this if a is the variable? Derivative of a would be 1. The derivative of v would be 0. So this chain rule, there is a chain rule in there, but it's just a 1. Okay? So we really wouldn't even have to write it down. Okay? So here's my derivative with respect to a. And now I need to multiply by dA, which I will just right now just put dA. We'll find the value here in just a second. Okay? All right, plus. Okay, I need the derivative with respect to b. This will be the easy one here. Okay? If b is the variable, so in other words, I've got something times b, what's the derivative? It's just the something, right? Okay, if I have 10 times b, the derivative is just 10. Okay, so a minus v to the negative 1 times b, the derivative is just a minus v to the negative 1. Okay, and then I multiply that by dB. Okay, plus, then I go after the cv. I go after the partial with respect to v. Okay, all right, derivative with respect to v. It's going to look a lot like the first derivative here. I'm going to have a negative b times a minus v to the negative second. This time, though, what's the derivative inside here? Derivative with respect to v is what? Negative 1, right. So negative 1 is my chain rule times dv. Okay. And now it just becomes a big arithmetic problem where we have to sub in all the correct values and do the calculation. All right, the opposite of b is negative 200. A minus v squared in the denominator. Okay, so a minus v squared. So that looks like 35 squared because 160 minus 125 is 35. So 35 squared times 1 times dA. All right, what's my dA in this problem? Negative 15. I started here and I changed it to this, so I lost 15 units. So times negative 15. Okay, plus then I go after the second part. A minus v to the negative 1. Okay, that'll be 1 over 35. Okay, this will be the same 35 all the way through here. Okay, times dB. What was my dB on this problem? Negative 10. Okay, plus negative b, so that's still negative 200. 35 squared, just like before, times negative 1. So since it's a negative 1, I'll just put a plus right here. And then dV was what? 5. I went from 125 up to 130, so I increased by 5 units. Okay? And then we just have to punch this in the calculator and see what we come up with for an answer. Okay? Right? So whatever number you come up with for this point, what would we do to finish off the problem, though? Because we're not quite done yet. This is just the DC. What do we have to do to get this final answer right over in here? Just say this happens to come out to be 10, just to pick a nice number here. If this is 10, what do I need to do to get this answer here? I have to add it to the value of c, right? Okay, just like we did on these previous examples. We found the value of z, and then we added it to whatever the change came out to be from our derivative. Sure. Okay? All right? And so you have a couple more calculations to do, but it just becomes a matter of punching them in there to get the answer. Okay? All right. One more example here. All right, it says that the height of a triangle is measured as 42.6, and the base is measured as 23.4. Okay, so we've got a triangle. It says the measurement of the height can be off by as much as 1.2. So the height could be off by 1.2 centimeters, and the base could be off by no more than 0.9. And the question is, estimate the maximum possible error in the area of the triangle. Okay. So what is our initial equation to start with on this one? 1/2 times base times height. Okay, we're starting with the area of a triangle, just 1/2 base times height. We want to use differentials to approximate if our measurements can be off by this much. And again, it's very common real world that your measurement that you want might be this, but you could be off by a little bit. And so we need to estimate how much error that could possibly create in the end of the situation for us. Okay? All right. So dA in this problem, if I just had to write out the formula, would be take the partial derivative with respect to one of the variables times the dB for that variable plus A sub h times dH. Okay, so we take each partial derivative times the d for that particular variable. All right, what is A sub b for this problem? What's the derivative of this function if b is the variable? 1/2 h, right. Okay. dB in this problem is what? Now, dB is how much can the base change by in this question? And what's the answer? 0.9, right. The base can only be off by 0.9. Now, we don't know if it's positive or negative, but we'll just go ahead. Since the question wants the maximum error, we'll go ahead and just let these all be positive values. Okay, so the dB could be off by 0.9. Okay, okay, plus A sub h. What's the derivative with respect to h? Yeah, just 1/2 b. And how much can the height be off by? 1.2. Okay. Now, the only other thing left to do is to sub in the values for h and b that we were given in the problem. These were the ideal values, or the nice values, okay, according to our previous problems. So we've got 1/2 times 42.6 times 0.9 plus 1/2, 23.4 times 1.2. And we punch this in the calculator. Now, the question wants to know, estimate the maximum possible error in calculating this area. So once I get this answer, whatever it comes out to be, for this particular problem, that is the answer. Because they want to know what the error is. They don't want to know what the new area of the triangle is. They just want to know how much error is possible. And if this is the error, remember error was dH and dB. If I want to know the error in area, that would just be the dA value. So I don't necessarily need to do any addition at the end. Okay? All right. We'll see you next time.